In this video, we'll be talking about how to sketch the graphs of rational functions. Alright, in summary, the easiest way to sketch the graph of a rational function is first to factor the top and the bottom, as we saw in the last video, and create and cancel any common factors. This creates holes in the graph. Again, I talked about that in the last video. Secondly, we also then go through and find the y-intercept using f of 0. We also find the zeros of the numerator, and these are going to be the x-intercepts, because we know that the whole function is 0 if and only if the numerator, aka the top, is 0. 4, we find the zeros of the denominator. These are going to be our vertical asymptotes. 5, we find and we sketch the horizontal asymptote. And then 6, we go ahead and we plot additional points in between the above info to help us sort of sure up the graph, so to speak. And then finally, we graph a smooth graph that incorporates all of the above information. So for example, let's go ahead and sketch the graph of g of x equals 3 over x minus 2. Well, what we notice here is this is exactly, here going through our information, it's already factored, so done with that. Plugging f of 0 in for our y-intercept, what we get is negative 3 halves, y equal negative 3 halves. So let's go ahead and mark that on our graph. Negative 3 halves is right there. Then what do we do? Well, then we find our x-intercepts. There are no x-intercepts because the top of the top is never 0, so none. Vertical asymptote, we can find. Vertical asymptote, we have that the bottom is 0 when x equals 2. We have a horizontal asymptote is going to be y equals 0 because the degree of the top is less than the degree of the bottom. So, in other words, that gives that y equals 0 is a horizontal asymptote. And then finally, we need some extra points. Well, let's go through and look what we have so far. So far, we have that point. This is a horizontal asymptote. We have our vertical asymptote at x equal 2. We also have, so then we also have what? Wait, that's everything. Yeah, no, that's everything that we have. Good. So we go ahead and we pick some extra values. Let's look at some x and see what happens with g of x at those spots. For instance, let's go out here to negative 3. We have negative 3, negative 2, negative 1. 0 we've already seen. 1, 2 we already know that's a vertical asymptote. 3, 4, and that should 3, 4. Let's look at 5 as well. Okay. 6, why not? Alright, plugging negative 3 in, we get 3 over, negative 3 minus 2 is negative 5, so negative 3/5. Plugging negative 2 in, we get negative 3/4. Negative 3/3 when plugging 1 in, so negative 1. Plugging positive 1 in, we get 3 over 1 minus 2, which is negative 3. Plugging 3 in, we get 3 over 1, which is 3. Plugging 4 in, we get 3 over 2. Plugging 5 in, we get 3 over 3, which is 1. Plugging 6 in, we get 3/4. And so what do we see by plotting those points? Well, negative 3/5 is, so at 3, 1, 2, 3. Negative 3/5 is a little bit bigger than 1/2, so about there. Here we see negative 3/4. It's about right there. Negative 1 we can see is right there. We already saw that point. 1, 2, 3. At 1 is negative 3. 1, 2, 3. Over here we see 3 at 3. 1, 2, 3. 1, 2, 3. 3 halves, so about there. Then 1, and then 3/4. And so what we see is indeed the graph, if we were to pick more points, we would see this better. But the graph kind of wants to go up here. It wants to go down on this side. Yeah. And get really, really close to that line. Here, it wants to get really, really close to the x-axis as time goes on because that's our horizontal asymptote. And similarly here, it wants to get close to there because that's our horizontal asymptote. All right, so that would be roughly what the graph looks like. There is, however, a better way to see this, which is that this is really a transformation if you have for f of x equal 1 over x. What we see is that g of x, which we can factor out the 3, and then we have a 1 over x minus 2, and thinking of it that way, what we actually have is that is 3 times f of x minus 2. In other words, we're taking the graph of 1 over x, which we know looks roughly like this. We're stretching it by a factor of 3, and then we're moving it 2 to the right. And so we can see that function transformations allows us to do that as well. Now it's time for you to try an example. You can use either of the two ways. I suggest trying both of them. But go ahead and sketch the graph of f(x) equals 1 over x plus 3. On the count of 3, I'll reveal the solution. 1, 2, 3. So here we can see that really the better way to do this is to recognize that's just a shift of 1 over x to the left by 3. But if you use all the information, you get this as well. I graphed the points, vertical asymptote, horizontal asymptote, all of that stuff. And so it would look like that. So let's do another example. Let's go ahead and sketch this graph. Again, it's already factored for us. We see that the y-intercept, plugging 0 in, gives us, there is no y-intercept because that's precisely where the vertical asymptote happened. So none. X-intercept is where the top is equal to 0. 2x minus 1 equals 0 means that x would be 1/2. Right, because that makes the top 0. We also have what? We also have that vertical asymptote is when x equals 0. Horizontal asymptote, well, the degree of the top is equal to the degree of the bottom, which means it'll be the leading coefficient, so y equal 2 over 1, or 2 if you prefer. All right. We also have that what? We would also have, so now we need some extra points. X equal 2, we have a vertical asymptote there. We see x equal 1/2 as an x-intercept. X equals 0 is 1. What we have also is, so picking some extra points. Picking x equal -3, -2, and -1. What happens? We get, so let's go ahead and draw our horizontal asymptote as well. X equal -3, -2, -1. 0, we know what happens. 1, 2, and 3. Why not? We'll make it nice and symmetric. Plugging -3 in, we have -6 minus 1 is -7 over 3. So -3, so 7/3. Plugging -2 in, we have -4 minus 1 is -5 over 2. So positive 5 halves because it's -2. Plugging -1 in, we get 2 times -1 is -2, minus that is -3, so over a -1, so positive 3. Plugging 1 in, we get 2 minus 1 over 1, so 1. Plugging 2 in, we get 4 minus 1, which is 3, 3 over 2. And then finally, plugging 3 in, we get 6 minus 1, which is 5 over 3, so 5/3. So let's go ahead and graph all of those. graphing all of those gives 7/3, which is where? So that's 2 and 2/3, -3, so 2 and 2/3, right? Yeah. 1, so 1, 2, and 2/3, just about there. 5/2 is 2.5. 1, 2. No, that's, yeah, 2 and 1/3, sorry. So if that's thirds and that's half, that would be about there, but this would be a little bit higher up. There we go. Sorry about that. Here, then we got 3 when we plugged -1 in. When we plugged 1 in, we got 1. Then we got 3/2. Then we got 5/3. And so what we see, not surprisingly, is that this has a vertical asymptote there. The horizontal asymptote it's going to want to become part of. Here, vertical asymptote. Horizontal asymptote. And here again, I'm drawing the line there because really, if you were to actually graph this in Desmos, you'd see that it gets really, really close to that line. So you'd have to zoom in. It would look like it actually flattens out and becomes that line, but it just gets really, really close to it, and so it's hard to see. Okay? Of course, there is actually a better way to do this. You can still use the better way. It's a little harder to see here, but if you think of 2x minus 1 over x as, if you do a synthetic division here, that would be 2 and 1 divided by the 0 at the bottom, which is 0, 2. 0 times 2 is 0, and 1 is that. Oh, -1, so -1. So I end up with 2 minus 1 over x. What I notice is that, in other words, I take this and I add, or you can think of this as -1 over x plus 2. So I do a reflection, right? I do a reflection and then shift up 2, right? By 2. So it is still a transformation of 1 over x. And now it's time for you to try an example. So go ahead and sketch the graph of g of x equal 3 plus 2x over 1 plus x. On the count of 3, I'll reveal the solution. 1, 2, 3. So here, again, using all the information, you get this. Here, there is the better way by doing the division. You can get that as well and see that's just shifting around 1 over x plus 1, or just 1 over x. All right, finally, we're going to look at a little bit of a harder example to work. So let's go ahead and sketch the graph of fx equal x over x squared minus x minus 2. Here, plugging 0 in, we get 0. So we have a y-intercept of y equals 0. Of course, that's also our x-intercept is x equals 0. Factoring the bottom here, you can see that this is really x. I should have factored at the start, but that's x minus 2 and x plus 1. So the vertical asymptote is going to be x equal 2 and x equal -1. So we have 2 different ones. And finally, we have our horizontal asymptote. A horizontal asymptote, because the degree of the top is less than the degree of the bottom, we have that is going to be y equals 0. All right. Well, now that we have that, let's go through and plot what we have so far. So vertical asymptote's at 2. At -1. And finally, at we have this is that. We also have, okay, so at 0, we have our one and only intercept. And what happens in between here? So now we kind of have an idea of how to pick points. Well, we have, let's look at this. So we have, by the way, we can't do long division here, so this will not be a transformation of 1 over x. You can try if you want, but you won't get anywhere with it. Here, if we have x and we have f of x. Here, let's go ahead and pick some points. 1, 2, 3, 4. Let's do -4, -3, -2. -1 is there. Let's look at -1/2, because I'm interested to see what happens in between here. -1/2, +1/2, 1, and 3/2. And then finally on the other side, so 2. Let's look at 3, 4, and 5. All right, that's a good set of points. Plugging -4 in, we get -4. We get 16 plus 4 is 20 minus 2 is 18. Plugging -3 in, we get, that can't be right. 1, oh, no, 4 over 18. Sorry. 4 over 18, which is roughly 2 over 9. -4 over 18, so -4 over 9. 2 over 9. Sorry about that. We also have plugging -3 in, we get what? We would get -3 over 9. 9 plus 3 is 9 plus 3 is 12, minus 2 is 10, so -3 over 10. If we plug -2 in, we get -2 on top, we get -2, so that would be 4, plus 2 is 6, minus 2 is 4, so -2 over 4, so 1/4. Is that -3 over 10? -3, 9, 9 plus 2 is 12, 9 plus 3, no, 9 plus 3, yeah, okay. -1/4, sorry. Right, because 2 squared is 4, minus plus 2 is, 2 squared is 4, plus 2 is 8, no, sorry, yeah, 1/4, yeah, okay. Plugging -1/2 in, so let's go ahead and start plotting some of these points. We have -2/9 is really small. -3/10 is also quite small. -1/4 is about there. So it looks like, because I know I can't cross across the x-axis there, it looks like this is what's happening. Okay. On the other hand, -1/2, plugging that in, I will get, oh, let's think of it. Let's, we have 1/4 plus 1/2 is 3/4. Minus 2, 3/4 minus 2 is -5/4. But that's divided by -1/2, so 5/2. Positive 5/2. Plugging 1/2 in, we expect a negative answer. We'll have 1/2 divided by 1/4 minus 1/2 is -1/4. -1/4 minus 2 is going to be -9/4. -9/4, so -9/2. Or -2/9. No, -2/9. If I plug 1 in, I get 1 over -1. -1 times 2 is -2, so -1/2. 2/9 is itty bitty. It's like right there. 1/4 is like right here. That's positive 2/9, sorry. That's right, yeah, that's right. 5/2, right. So 5/2 is like right there. So this will become like that there. 1/2 is about here. Oh, let's skip ahead. Plugging 3 in, we get 3 over 3 minus 2 is 1, 4, so 3/4. Wait, 3. Yeah, 3/4. Plugging 4 in, we get 4 over 4 minus 2 is 1. Sorry. 4 minus 2 is 2, times 5 is 10, so 4/10 or 2/5 if you prefer. So I'm just kind of going in and shoring up the graph a little bit. 5, plugging in, you get 5 over 3 times 6 is 18, so 5 over 18. In other words, what you get is 3/4, 2/5, so it's going to drop really quickly. But it should be going up this way as well. Okay, so that's roughly what the graph looks like. And now again, it's time for you to work a problem, so go ahead and sketch the graph of f(x) equals 3x over x squared plus x minus 2. On the count of 3, I'll reveal the solution. 1, 2, 3. And there you have a rough graph of it with the accompanying work. Alright, finally, let's do an example with a hole. So, let's go ahead and sketch this graph. Here we see that this is really... Oh, excuse me. If we factor the top and bottom, we have x plus 3, x minus 3. If we factor the bottom, we have x minus 3 and x plus 2. What that gives us is that gives us a hole, because these cancel, when that was 0, so x equals 3. When x is 3, we get a hole. Let's go ahead and find the y-coordinate there. What is our y-coordinate? Our y-coordinate, plugging 3 in, would be 9 over 6, so 3/2. No, 9 over 5, sorry. 9 over 5. 5. Good. Alright, sorry for that. Hit a bit of a hiccup with this example, but after you do all the information, you get a hole from canceling the factors. Plugging in, finding the rest of the information, you get this. I strategically pick points, and thus, plotting these points, I get 1/3, which is about there. I get -1, which is there. I get 2 here. I get 5/3 there, and I get 7/5 here. So, connecting the dots. Get that. It becomes like that. This, we know, will asymptote. Alright, and so you end up with that sort of a graph. Once again, it's time for you to try, so go ahead and try out this example for yourself. On the count of 3, I'll reveal the solution. 1, 2, 3. So here I employ a bit of a more clever strategy. I recognize that I get a hole when x equals -2. I saw this before in my earlier example, so when x is not equal to, I go ahead and I plot my hole. Then I do the long division, recognize I can just shift around 1 over x in the following way. So I end up with that. For more practice in graphing rational functions, and sorry for the long video, be sure to see page 175 of the textbook and work problems 17 through 38. In our next video, we'll be looking at slant asymptotes.